Hello everyone, I'm back again. Today I thought I do want to do a story about Saturn V, so we'll call it Saturn V. These what I read are true. They're from the 1970s, but as you know, information is embellished and over exaggerated nowadays. So I thought I'd start this channel and I can start reading more accurate information, which is sort of more reliable from my perspective. So anyway, and I'll also ask you if you like it, if you don't mind, press the like button, please. And if you like it even more, then subscribe if you don't mind. I'll start. So I'll call it. This is called Saturn V. Blasting off a Saturn V rocket is the equivalent of setting off an explosion under a naval destroyer, balanced upright on its stern and blowing it more than 30 miles into the air, but so smoothly that no fragile object on board is broken. The rocket, the biggest operational one in the world, was designed and built to get man to the moon. It has 2 million working parts and, for launching, each is monitored electronically from a control centre 3 miles from the launching pad. At the control centre, 400 men and women sit watching television screens and instrument panels, but the final word rests with 3 small computers on board the rocket. Two of them must vote yes before a clock starts ignition in the engines and the rocket lifts off. The stage is assembled. The Saturn V is constructed in 3 sections, each made in a different part of the United States, and transported by barge, road or air to the John F. Kennedy Space Center in Florida, which I think is not in use no more, but I'll carry on anyway, to be put together. Final assembly and checkout is done in the vast vehicle assembly building and takes at least 4 months. The first stage, 138 foot tall, 33 foot inch diameter and weighing 130 tons without fuel, is placed upright on a 6-legged platform alongside a servicing tower. The second stage, 81 foot 7 inches tall and weighing 43 tons, is lifted on top by crane. Stage 3, 58 foot tall and weighing 16 tons, is hoisted on top. Finally, the spacecraft itself, which might possibly carry 3 astronauts to the moon, is placed on the very top. An Apollo spacecraft is 82 foot high and gives a total height of about 360 feet. Only when the spacecraft nears its destination will stage 3 be jettisoned. The whole rocket is fitted together vertically and moved to the launching pad with its service tower clamped to it. The crawlers that carry out this huge task are the world's biggest land vehicles. There are only 2, both at the Kennedy Space Center. Everything about them is colossal. They weigh 3,000 tons each, are 131 foot long and 114 foot wide, have a crew of 10 in a driving cab at each end, and do the 9-hour journey to the launching pad at a majestic 2 miles an hour, tackling gradients of 1 in 20. Each crawler has 18 engines, including 2 which develop 2,750 horsepower. Then there are generators, hydraulic power units and electric motors for driving the tracks. Starting up a crawler takes 90 minutes. The manual on how to do it is 39 pages. Each link of the 8 Caterpillar tracks weighs a ton, and the special roadway to the firing pad sinks an inch each time a laden crawler passes over it. As the crawler and rocket move slowly towards the pad, a complex jacking and levelling system keeps the ungainly load level. When the rocket is at last unloaded, it is filled with 12 million gallons of liquid hydrogen, liquid helium and liquid oxygen. The fuel is poured into cold storage tanks so well insulated that ice cubes would take 8 years to melt in them. With the fuel loaded, the weight of the rocket is increased to 3,000 tons, heavier than a destroyer, and it sinks 16 inches into the brick-lined pad. There are 11 main engines on a Saturn V for upward thrust and another 22 for steering. Each of the 5 engines in the first stage weighs 10 tons and consumes 3 tons of fuel a second, pushing with the combined power of 30 diesel locomotives. Together they generate 160 million horsepower. They take the rocket about 38 miles up and boost its speed to more than 6,000 miles per hour. Then the second stage engines ignite, raise it to an altitude of more than 100 miles and increase its speed to 15,000 miles per hour or more. The fuel pumps need turbines generating 300,000 horsepower, twice the engine power of a liner. The third stage contains only one engine, but it can be restarted. This engine is used for putting a Skylab space station into orbit or sending a spaceship to the moon. It can boost speed to 25,000 miles per hour. The conical command module has no propulsion system of its own, but it does have small control jets to position itself for re-entry to the Earth's atmosphere. So far, Saturn V has made 13 almost perfect flights. This information is from 1976, so I'm just letting you know. The first men to land on the moon were lifted off Earth by Saturn V, but when the next flight of this gigantic rocket will be is uncertain. The Americans are keeping 2 rockets in mothballs for when they are wanted. That's the end of that story. I'll do one more for now. This is about hydrogen, the use for how you can the use for hydrogen fusion. So this is about hydrogen fusion. So we'll just call this hydrogen fusion. There we go. There is enough hydrogen in 1 gallon of seawater to provide as much heat as 10,000 single bar electric fires burning for 1 hour. Scientists all over the world are now trying to harness this energy by a process similar to one that occurs on the surface of the sun. This is called continuous thermonuclear fusion and involves causing hydrogen atoms to rush together and release vast amounts of energy. The process is vastly more powerful than the energy created by nuclear fission, which involves breaking uranium atoms apart and was used in the first atom bombs. The fusion has already been achieved to a degree in the hydrogen bomb, but H-bombs, like the sun, are an example of uncontrolled thermonuclear fusion. What the scientists are seeking is a way to harness the energy safely for peaceful purposes. Hydrogen nuclei do not fuse readily, but if the temperature of their surroundings is increased sufficiently, they rush together and fusion takes place. Raising the temperature is not easy. About 100 million degrees centigrade is required and has to be maintained for about 1 second to start the reaction. Once the hydrogen atoms are fusing, the reaction has to be contained so that it does not explode and allow the energy to escape and be wasted. So far, the nuclear scientists have been unable to maintain the reaction for more than a fraction of a second, but they are confident that the problems can be overcome and that by the year 2000, remember, this is from 1976, the first thermonuclear power station will have begun operation. The sea will provide an almost unlimited supply of hydrogen, and it can be simply and cheaply extracted. See, we haven't got this today, and look where we are, 2024. So, well, anyway, I'm telling you some good stuff here, so I'll keep reading. While a modern coal-fired power station needs 10 trainloads of coal a day, a thermonuclear station could operate for a day on the hydrogen from one single water truck. Well, I'll do one more story. This is called Lightweight. I know we're in the 2000s now, but like I said, this book is from the 70s. So I'll say this one. This is about fuel cells, lightweight alternatives to making batteries. A major problem in space travel is providing power to use inside the spaceship. It is needed for instruments, heating and cooling systems, computers, radios, TV cameras and other equipment. A trip to the moon would call for something like 40 tons of conventional car batteries and a generator. The hydrogen-oxygen fuel cell is a lightweight alternative. that also provides drinking water as a byproduct. 3 of the cells were installed in each Apollo spaceship which went to the moon. A fuel cell is a type of battery which makes electricity instead of storing it. A hydrogen-oxygen mixture, or oxygen acting on a fuel such as carbon, creates current at 2 terminals. As long as the gases are fed in the cell, continues to produce electricity. In a spacecraft, both gases can be produced from water and they recombine to form water again as they produce current in the cell. It is a cycle that can in theory go on indefinitely. However, since the energy released in the cell is less than the energy required to produce the gases from water, in practice cells are normally powered from gas cylinders. Fuel cells developed by Francis Thomas Bacon, an English engineer, offer many possibilities. Electric trains that need no overhead wires or trackside live rail, buses and cars that do not emit fumes, silent generators and lightweight power packs for spacecraft. The main problem in adopting the cell for use in everyday life is cost. Although hydrogen and oxygen are cheaply available, catalyst materials which help the reaction are expensive. The market price of platinum, the most efficient catalyst, is about £80 for just over an ounce. Now I think that might be a couple of grand in this day and age. Right, I'm going to leave it now. So I've just read 3 stories for you, but if you like these stories, I'll keep on reading them and post every day or two. So I hope you enjoyed them anyway. Thanks for watching. Thank you.